Hi there, this is Dr. Mark Snyder. This is COP 1000, and let's jump right in. The textbook for this semester is the one that you see pictured there in the upper left, the Programming Logic and Design 10th edition by Joyce Farrell. We used to use one called Programming with Python. This course will be mainly about how to learn to program, the introduction to programming, and we use Python as the language. But we've recently upgraded to the Farrell textbook in order to give you a better experience, introduce additional topics outside of just Python language that pertain to introducing you to the world of computer programming. And I think it's a good one, and we still have just as much material to draw from regarding Python. So it should be a good semester. So one of the first things that you're going to want to do, probably the way that you found the link to this video, was by looking in Canvas. One of the first things it will direct you to is to the Modules tab, and inside the Modules tab there will be a number of activities for you to peruse to get started with the class. The very first one that we recommend that you do is the attendance verification quiz. That one is inserted by the university, and it is the one that is required for you to verify that you're attending class in order to get any financial aid sign-offs that might be required for you for the semester. The next thing you want to do is make sure that you have access to the resources for the textbook. This is a Cengage textbook. The college is in a transition between various Cengage resources and BiblioU, so at the time that you're watching this video, just look for the link in Modules for the textbook, click on it, and make sure you can get in and you can see the material that we have selected for you. The next thing that you'll want to do, we're going to create various files for the projects that are assigned for the semester. And programming is an active learning exercise, and you'll be performing skills and creating files and turning them in and getting them graded throughout the semester, and you'll want to come up with a strategy for how you're going to manage those files. The easiest low-tech version of this would be just to carry around a flash drive with you all semester with the files on it. You might be using OneDrive or Google Drive or some semblance of that, or any number of other places where you store your files, but you'll want to make sure that you have access to those files whenever you come to class or come to school to use a school computer, and you sit down and you log into the school computer. You'll need to figure out how to access those files from there, whether it's plugging in your flash drive or logging into OneDrive, whatever. And same then at home, whatever work you do at school, you want to be able to bring that home and pick up where you left off with your editors at home. So that'll be the next thing that you'll want to put on your to-do list to figure out how to do. And we'll do some easier assignments at the beginning to make the assignment part easy, so that you get practice doing get the muscle memory for how to manage your files and turn them in. That's the next bullet point, is we turn our projects in through the Canvas portal, logging into going to Modules, clicking on the assignment for that unit, and there should be something there that says upload files, and that's what we'll want to do. Make sure you check back with Canvas regularly. Sometimes there are changes even during the week that we're working on a unit. I might add some reading material or add a discussion topic for you to go out and complete and discuss some topic with your fellow students. So keep on top of that regularly. A couple of times a week probably would not be too much to check in on Canvas. The great thing about Canvas is if you log in, it will show you on your dashboard the upcoming assignments and the due dates and things on them. The next thing will be my office hours. I typically every semester will post office hours, and some of them will be online, some of them will be on campus, and whichever way you prefer is fine with me. That's, again, my preferred office hours. Best way to get a hold of me if you have a question is just to email me. You can do that through Canvas also. And if you need to get in touch with me, just because I have office hours posted, I have meetings and classes that I'm in and different activities around campus. So the best thing to do would be to contact me and set up an appointment for getting together and chatting about whatever you want. But like I said, best course is to try email first. Most questions I've heard multiple times, and I can answer, and we can clear things up via email if need be. So I don't go too much into my background. You can see my LinkedIn profile link there. I have about 40 years of experience in the industry. My PhD from the University in Missouri that's shown there. I've worked at a variety of different companies, from airlines to some time at Microsoft, about 10 years there. I've worked on a variety of different computer languages over the years, and I do have a life, or try to, with my family outside of work, and so you can see some of my activities that I enjoy doing outside of work listed there also. The main reason that I put this out here and suggest that you get to know myself and your other professors at school is not to stroke our egos or so that we can tout all of our accomplishments over our career. It's mainly so that you can find out how my background, my experience meshes with your goals for your career, and start thinking about ways that I might be a resource to you. If you need to ask me a question, if you go to a job interview and they ask you a question and you weren't sure what the right answer was, you can shoot me an email and I can try to offer some of my experience over the years. I was a hiring manager at various different companies and interviewed people like yourself, and it's getting a job is a skill, just like learning to program in Python is a skill. You don't start out just being good at it right off the bat, and it does take practice to get good at it. And you want to go to a lot of different interviews, as many as you can, in order to practice that skill, because one of these days you'll have an interview for a company that you'd really like to work for, and you want to have that experience under your belt by then, and so that you can do your best at that interview and give yourself the best chance to get that job that you want. So what is this semester going to be about? Well, like I said, we're going to be discussing Introduction to Computer Programming. We're going to use Python as a example program. I'll probably pull in concepts and techniques and patterns from other programming languages, especially where some other language supports an important concept that Python doesn't do well, or doesn't do the same as what is typical for a computer language. Then I'll bring in information from other languages. But in short, computer programming is solving problems. There's a lot about computer programming that involves solving puzzles, and a lot of people like solving puzzles, and so it takes that drive to keep at it and find a solution and be creative and trying different things until you find something that works. And even once you find something that works, trying to think, could I have done that a different way that might be more efficient? And so problem solving. So when we're programming a computer, we're developing algorithms. Algorithms are a solution to a problem written in source code. So the task of programming is iterative, meaning that you're not going to sit down and expect to write the code the first time and it just magically works. We will write some code, we'll test it, we'll debug it, fix those bugs that we find, and we'll keep iterating until we make it as complex as it needs to be for the problem that we're trying to solve, and then we'll say we're done and we'll turn it in. I would say also that this is a lifelong skill. It's not something that you can take a semester course from me and then, okay, great, I learned that skill, now I can move on with my life and do other things. You need to expect to continue learning. Our industry is one that is constantly changing. The languages and patterns that are popular today and necessary for your job today may not have existed 10 years ago or 20 years ago. Likewise, the things that were crucial to know 10, 20 years ago are not even applicable in many ways today. So it's important, and even I watch YouTube, I read websites, I acquire books, and I read them to stay current on what the state of the art is in the industry. It is artistic and creative. It combines the analytical side of your brain with the creative side of your brain, and I think that that's one of the things that makes it really fun. So, when we're talking about going to the doctor, a doctor might say that they practice medicine, and I think we should probably use the same terminology or same phraseology when we're talking about programming, that we practice programming, that we're never perfect at it. There may always be a better solution out there than the one that we came up with, and then we just continue. We continue learning and practicing. So people have different misconceptions when they come to try to learn computer programming, and I've offered a few there. So some people think that, if I learned to program a computer, that means I can create web pages. It's slightly different than that. Some people think, I really love playing games, and my parents told me, if you love playing games, you should probably go learn computer programming. It's more than that. It's often, almost always, easier than it seems at first, which to me, all worthy skills are like that. Whether it's golf or baseball or drawing, painting, whatever it is, you would hope that it would be something that you can't master instantly. That way it presents enough of a challenge to make it interesting to pursue. And there's many more skills than we can learn in one semester, so don't expect that you're going to master it. And I would not try to overload you with so much that to make it more than you can handle. I've told many people that I've never met a student that couldn't program a computer, that couldn't learn how to do this. I've found a number of students over the years that once they learn what programming is, they realize, that's not something that I want to do. That's perfectly fine. But don't go into this thinking that this is something that I probably can't do or I might not be able to do. You'll probably figure out how to program a computer, and then you'll decide whether it's something that you want to base your career off of or you want to go pursue other things. So some of the skills that we're going to work on and acquire and practice this semester, first is pseudocode. So we're going to read and write pseudocode. What is pseudocode? Well, it's kind of code. So it's not something that the computer is meant to understand. It's a way that we communicate to one another how we're going to solve a problem. If I have a tree in the backyard and I want you to cut it down, but I said, but hold it, before you go rip it and tear it, can you explain to me what your approach is, how you intend to cut the tree down? Well, I'm going to go look for buildings that it could fall on and try to find a place where I think it'd be safe for it to fall. I'm going to get my chainsaw, I'm going to cut it this way. Those are examples of a form of pseudocode for explaining your algorithm for how to chop down that tree. And similarly, when we get ready to write a program, it's often it's easy to rush in and start writing code too quickly before we've thought through to the end. And in programming job interviews, they call this not asking clarifying questions. They usually make the instructions or their question that they ask the interview candidate intentionally vague to see whether the candidate will ask clarifying questions and get more information before they just rush in and make some assumptions and start writing code. So by stopping and thinking through our problem solution and expressing it in pseudocode, we're just taking a moment, take a breath, and say how we intend to solve this problem before we jump in and start doing code. Flowcharts is another skill that we're going to acquire. Similar to pseudocode, it's an expression of what our solution is going to be. However, it's a graphical solution. It's a diagram instead of just text. You can compare this, the analogy would be where a pseudocode might be a written set of directions on how to drive to the store, a flowchart would be a map of how to get there. They're the same thing. They're ways to express an algorithm, but one is text and the other one is a diagram. We're going to learn procedural programming using structured languages, namely Python. And when I say that, I'm making a distinction between object-oriented, event-driven, asynchronous, etc. You can Google what those words mean if you don't know. But I'm trying to be very precise in my words there to limit the scope of the class to let us focus on things instead of just going this direction and that direction and confusing you. We're going to focus on procedural programming. Procedural basically means my programs are always going to start at the beginning. They're going to go step by step in sequence until they finish what they're trying to do, and then they're going to complete. As opposed to, like a quick example would be an event-driven program would be like a Windows program, where often it's sitting there idle, waiting for you to click a button or press a key on your keyboard. And when you invoke one of those events, an event handler will awaken and handle what just happened. But most of the time they're sitting there idle waiting for something interesting to occur. So we're not going to do that kind of programming in this class. We're going to stick to procedural programming. The next skill is we're going to do lots of analyzing problems and developing solutions. And like I said, that's what we refer to as an algorithm. I keep using that terminology to make sure that I pound it in and that you hear it a lot. And I remember a quick story back when I was first learning how to program a computer in high school. And I asked my teacher one day, I said, what is it I'm planning on being when I grow up, using all of this information, these skills that I'm learning? And he thought for a minute. He said, well, you're probably going to be looking for a system analyst job. I had no idea what that meant at the time. Well, now I do. In a broader sense, we solve problems. Whether you're standing in a line at a bank, that's what we old people used to do. We would go to a bank physically and we would sit there in a line and wait for the teller to help us. So sorry about the old guy analogy there. But standing in line, let's say at Chick-fil-A. I'm standing in line at Chick-fil-A and I think, if they set up this line a little bit differently, or they had more cashiers or fewer cashiers, then they might be able to process more customers per hour. That's just a very trivial example of me looking at a system and analyzing it for possible optimizations. And that's what system analysts do in general. And the skill of being a system analyst applied to programming a computer is where the computer programming skill comes in handy. You got to know the language in order to develop the algorithms to fulfill your solution as a system analyst. So I've got a little bit of a demo here to show you of a console application running, and this will give you an example of what it is you can expect out of a program. If I can find the window. Okay, we'll just watch this once. So the window that you see this running in is it's a video of just a console window. Sometimes I might use the phrase command prompt, but in Windows and on a Mac, you can open one of these consoles and you can run your programs. And so let's start over. So I go to a folder where my program lives, and I use the Python interpreter to run my mlm.py program. It prints some headings and gives me some options for input. I select option A. It asks me to enter a name, an address, and a city, so I'm entering those pieces of information in order to add a record to my label maker program. So you can see here that it added the label. I can type the L key to list the labels that I've got, and then I can hit the X key to exit. Now that's a very simple example of a not very useful program. Well, I guess if you're trying to create a label, it would be very useful. But this is the kind of pattern that we're going to repeat over and over and over again. I'll give you an assignment. You'll create a Python program. You'll be able to run it from the command line. It'll ask for input. It'll do some things with that input. It'll produce some output, and then it'll eventually exit when it's time for it to. So we're going to do lots of programs that follow this pattern that look like this. And that's the reason why I wanted to show you that. And then the last thing that we want to do is make sure that along the way we complete these assignments in such a way that you build up your confidence. This course is a prerequisite for any of the FSW programming courses and several other courses in the degree program. And so I want to make sure that I give you the skills and the patterns to build a framework and a good base for you to jump off of to be successful in one of these classes. And when I'm thinking about your final grade at the end of the semester, that's going to be in the back of my mind. Has what you've done, has what you've demonstrated this semester given me the demonstration that you have a likelihood of being successful when you go on to your next class or not? And that's my job. Okay, as an outline for how we're going to accomplish this, and you'll see this pattern in many different programming language classes, so well-trodden ground here. The first thing that we want to do is, we've spent our whole life thinking like a person, talking to other people, and now we're going to have to try to talk to a computer. So the first thing that we do is we discuss how to think like a computer. How do computers handle memory, storing information, processing information? How do they get input? How do they produce output? We'll talk about a lot of those things and start getting to know the computer as a tool better, not just something maybe we play games on or compose Word documents or spreadsheets, but as something that we can use as a tool in order to solve problems that are interesting to us. So the next thing that we'll do is we'll start to communicating our designs to other humans, not to the computer, but to each other. And this is so that I can verify whether you have grasped the first topic, and we'll do some feedback there. And in communicating our design to other humans, we're preparing to be able to get more technical and more detailed as we learn more about what the computer requires to perform for us. But that's the next step, typically. So that's where the flowchart and the pseudocode come in. As you do more and more of these problems, it may seem like they're simple at first, but the very first pattern we're going to use is input, processing, and output. A computer program gathers inputs, it performs some processing on the data that it receives, and then it produces some outputs. Inputs, processing, outputs. I'm going to say that over and over and over again through the semester. So many of our programs that we're assigned to create are simply going to reinforce that. Well, first I need to get my inputs, next I need to do my processing, next I need to produce the outputs. The next thing we're going to do, there are tools, and we want to learn the tools. We want to test our programs. Those tools let us test our programs, and we want to learn common code patterns that aren't prone to bugs. Many different programmers over the years have taken many different approaches to solving some of these problems that we're going to pose, and some of the patterns have been accepted to be the right way to do it, and some aren't. Like when you button your shirt, You have to use the opposing button. If you're off by one, you're doing it wrong, and somebody will probably point that out to you at some point and correct you, and you'll learn to button it the right way. Very similar here. You may take a perfectly valid creative approach to solving a problem, and I may just gently try to say, okay, but that's not the way we do it typically. There's a bunch of other terms on this page, but it's, when you look back on the semester and you look at this list of topics again, you realize, oh yeah, that's generally the order that we proceeded throughout the semester. But at this point, I don't expect you to understand what all those things are, without Googling it or looking it up in the textbook. But we'll get there. We want to figure out how to get input and store it someplace for use later. We want to be able to put it in places and be able to do computation with that. And so that's what variables assignment computation is supposed to be saying. Conditional logic means we want our programs to be able to say, if this condition is present, do this, else do this. So that's what we mean by conditional. Repetition is we want to be able to do the same thing multiple times. So if I have a spreadsheet with a bunch of rows in it that contain data about my CD collection at home, I want to be able to do the same thing with every row of that spreadsheet repetitively. Modular program means that once I get a little piece of code, 5 or 6 lines of code that does something useful, I want to set it aside and put it in a place where I can reuse it if I need to, and we call those modules or functions or subroutines. We want to be able to read and write data from files. That's an important technique. There's some things particular to that most programmers know, and I want to introduce those to you so you're able to read and write data to and from files. Recursion, libraries, we'll get into those concepts as we go through. But that's generally the flow that we're going to go through this semester. This very first module corresponds with the first chapter in the textbook, but we're going to go over the components of a computer system as relates to introducing you how to program, understanding our computer, understanding it as a tool better. We're going to talk about simple program logic and go over how the book describes that. We want to get used to this thing called the software development life cycle. I think the book may call it the program development life cycle. I might refer to it as the homework life cycle. It's just a way you will approach each assignment. And you'll find after doing several of them how many pieces of it are just repetitive. You're just going to do the same thing you did for the last assignment, except for some particular parts. As said before, we're going to write pseudocode, we're going to draw some flowcharts, we're going to write Python programs, and then we're going to use the tools in our programming environment to process those and execute our code. Fun stuff. Okay, so jumping right in, a modern computer system has a number of components. If you look around your desk, you see a bunch of wires, you see a couple of monitors, you see a keyboard, a mouse, a little box that, all this stuff plugs into in some way, shape, or form, and maybe some other peripherals, maybe some speakers, maybe a webcam, different things that you find useful to be connected to your computer. That's all fine. Generally, we talk about common categories of these components, first being the CPU. It's a little chip inside your computer that does all the quote-unquote thinking for you. There are chips inside your computer that are memory chips. That is where all of the data is stored while it's being processed. We have storage devices like a hard drive. Often modern computers have SSD drives, which is solid state memory. In the old days it was slower and lower capacity. Now we have vast amounts of data storage capabilities in small spaces, and they don't take up much energy relative to before. We have input devices, so I would refer to the keyboard and mouse as input devices. The webcam is an input device. Your monitors are output devices. The sound card or the speakers are output devices. They output sound. What else? We've got some hybrid things too. If you look on your keyboard, often your keyboard will have a little light on it that indicates whether the caps lock is turned on or off. Well, even though the keyboard itself generally is an input device, if I touch the caps lock key, that light goes on and off. Okay, well, that little light is actually an output device. If the light is lit, that tells me some data. It reports to me whether the next keys that I type are going to be capital letters or lowercase letters. So there can be hybrids here. The webcam might be a combination device. It might have a camera for inputting visual data. It might also have a microphone for receiving audio data. So, there's a lot of gray areas to these categories, but generally I think you can hopefully get the point. We also have a category called connectivity. Your modern computer might have an Ethernet jack in the back that has the ubiquitous yellow or blue cable coming out of it that goes to your network switch or router. You might have Wi-Fi. You might have Bluetooth devices connected to it. All of these are using the connectivity features of your computer, and that's the way this one individual personal computer is able to communicate with the outside world through the network. So there's lots of different categories here. Okay, so software. We have different categories of software. First is system software. So your operating system, even underneath the operating system, there's a layer called the BIOS, and that is usually written in machine language, assembler language, very tight, very fast code that doesn't take up much space, but it basically lets the operating system itself talk to the raw hardware. So each of these pieces of hardware is going to have some software in terms of a driver that allows it to be communicated with in a structured fashion. So even your operating system looks for that layer of drivers and the BIOS in order to communicate with the hardware directly. The next layer up from the system software is application software. So things like Microsoft Word or Notepad, PowerPoint, these things are your web browser. These are application software packages. The programs that we write in here are going to be applications. They're applications developed by us, so they're more near and dear to our heart than at some anonymous corporation thousands of miles away that we had to pay for perhaps. But they're all in that class called applications. It's communication, or it's software that runs on top of the operating system that allows us to do useful things. Then there's this middleware. So just like with some of the hardware device categories where there are gray areas, in the software there's a category called middleware. It's not necessarily in the box with the operating system. It doesn't come with the operating system, but it's so intrinsic to the normal functioning of the computer, you might think of it and associate it with the operating system. But at the same time, it's not an application. It's not something we would typically interact with. An example I'm thinking of is your virus software. It's kind of in the background. You don't want to run a computer without some kind of virus software. Microsoft Defender comes with Windows, and it's usually doing its thing invisibly behind the scenes, and if everything goes well, you never even know that it's there. And you don't typically interact with it yourself, so you might mistakenly think it's part of the system software, even though in the way it's delivered and the way that you would interact with it, it behaves much more like an application software. So we kind of create a new category called middleware for those sort of applications. It sits in the middle. It's useful. We don't want to do without it oftentimes, but it's not something that we would call an application that we would commonly interact with. So what is software, after all? So as I said, we're going to be writing Python programs that are essentially application software. And so when we think of in terms of software that way, it becomes a little bit more clear that software is a computer program that is a program is instructions written by somebody like us, a programmer, and these instructions tell the computer what to do. Going back to our analogy, if I write somebody a set of instructions on how to drive to the grocery store, I'm giving the person a set of instructions that are meant for the person to execute. If I write a Python program, I'm writing a set of instructions that I intend for the computer to carry out those instructions. And I would approach those two activities in different ways. I would use a different language to talk to a human as I would to a computer using Python. So, as I said before, a program is going to typically do these three things, or at least this is what we're going to focus on for this semester. We're going to gather data as input. We're going to perform calculations on that data, move data around, copy it from one place to another, do different things with it, and then we're going to output the data, whatever our results are. Perhaps we're going to write that to a file, perhaps we're going to display it on the screen, whatever, but it's output. So that pattern of inputs, processing steps, and output we're going to see over and over and over again. There's a diagram called an IPO diagram that just makes you, again, take a second and you're given an assignment by your teacher. You stop and you pause for a moment and say, okay, reading the instructions for this, what are my inputs, what are my processing steps, and what are my outputs? An IPO diagram is nothing more than a list of what those three different things are given your assignment. Just a activity of getting organized, if you will, before you start writing code or even before you start doing any meaningful designs on your code. So these inputs may take different forms. There's a number of examples here on the screen that all would be categorized as inputs, and I would challenge you to try to come up with other forms of input that you can think of or that you've commonly seen a computer use in order to sense the world and when it boils down to it. Processing, there's a number of different things that a computer can do that we would classify as processing. The basic one that we're going to play with initially is I get a couple of numbers, a couple of integers, I add them together and store the results in a variable called answer. And we're going to hear that term variable used over and over. A variable is nothing more than a name that we give to a location in memory where we intend to store a value. So if I ask the user to enter an integer and the integer the user gives me an integer 2 and hits enter, and I take that value 2 and I store it into a variable named first number, then later in the program when I refer to the variable first number, I would expect to get access to the number 2 that I put there earlier. That's all a variable is. Name for a location in memory that's intended to store a value that has some meaning to us. You can see other examples there. The last one's kind of interesting. I get two strings from the user and I concatenate them together to make a new string of characters called, with the combination of those two words. Output is exactly what it says. So if I'm going to be printing hello world on the screen, the displaying the characters on the screen is considered output. If I display a window and it has an OK and cancel button on it, I have just produced some output. So even producing those buttons on the screen is considered output. I've given the user the choice of saying OK or cancel. The other examples out there. So the last statement here is kind of important, and it'll make a lot more sense when you start looking at the first assignment. But often in our programs we will say get a number from the user. Then when we go to write a program to do that, we're going to say, okay, to get the number from the user, I first have to prompt them to enter something. So I say, please enter an integer on the screen. And then I wait for them to enter something, and then they type some text and say enter, and I do something with that data to store it in a variable. Typical pattern. Okay, well, if you break that down to the lowest level of detail, I've done an output by saying, please enter an integer. Then I waited for the data to be entered, and the input is the step of taking the data and putting it in the variable. Now I've received input. But often we'll generalize that and we'll say, well, we'll consider that whole operation just an input. Prompting is assumed. We prompt the user for input and receive the input and put it someplace so we can use it later. That's all considered an input step. It can get kind of confusing when you get too detailed and too overly analytical about it, so beware of that. Another thing I would say is learn the patterns. So don't reinvent the wheel if you don't need to. Often I'm giving you examples because I want you to demonstrate that you've grasped something that we've been talking about. And initially that's going to be this idea of inputs, processing steps, and outputs. So when in doubt, organize your code around that pattern if you are endeavoring to get full credit. There are many, many ways to do this, but we don't need to get fancy with them right now. Things will get complicated soon enough. Right now we just need to follow the basic pattern. And in the beginning, in order to keep from getting blown away or overly confused about what we're doing, my initial expectations are you to just follow the leader. I'm going to give you an assignment. I'm going to basically show you what to do, and I want you to just follow the leader and do what I did. Then we'll progress. Once you've done exactly the way I said to do it, then we can move on to more complicated things, and you'll remember back, oh, I've done this part before, so that's not hard. I can just repeat what I did last time, and then we'll start adding new pieces that are more and more complicated. So another thing I want to talk about is where we find ourselves today. A little bit of computer history. The evolution of computers that I've observed in the 40 years that I've been doing this has been very interesting. You don't necessarily need to know this history to do your assignments in this class, but it's interesting nonetheless, and it's always a mystery where the computer industry is going to go from here. So I would like for you to temper your vision for the future with a little bit of history of what has come before. So in the beginning, the first computing machines, for example, I'm thinking about the kind of computers that they built in World War II to help defeat the Germans, or the computers that they built in the 60s to send the rockets to the moon, were all very simple. They were not the fancy advanced personal computers that we see today. Mostly they were just a bunch of wires connected together in what we would call logic circuits that performed very specific operations. The cathode ray tube, when it got invented, and a bunch more wires inside, not just the tube, but that was the forerunner of our modern computer monitors, and that display device let us see our data in ways that were familiar to us. We could see numbers and letters on the screen and read our data, as opposed to, you may have heard of punch cards. Reading the where the hole was on the punch cards was a very tedious way to read and communicate with our computers back then. But it was effective, and we did that for many years in order to do solve the problems that needed to be solved at the time. We eventually got additional peripheral devices like printers, speakers, and our computers just continue to evolve and become more useful to us as tools. Mainframes came along, and as these computers were getting more powerful, they also became more expensive, and some of these computers grew in size to take up entire buildings. So the pendulum swung in the direction of having fewer computers that were larger and centralized, and then dumb terminals. You might just have a cathode ray tube screen and a keyboard, no mouse, and the individual users would have these stations set up where each user had a monitor and a keyboard, but they were all connected and shared time on the one big computer that was stored remotely in a different part of the building. So that's what we call a mainframe with dumb terminals set up. Then things continued to evolve, and we got, the forerunners of our current personal computers, which put more power into the end user's hand. Instead of having a dumb terminal, they still connected to a mainframe, but then they had a much more powerful local device sitting on their desk that you could play, more interesting games with. You could run your own software that didn't need to be connected to the mainframe anymore. And then we eventually grew to have connectivity over the phone lines to other computers. Then we had networks, so we now have high-speed routers that can communicate at gigabit speeds per second. And then we went wireless, and we can communicate even faster over cellular airwaves or Bluetooth airwaves. So then once we had these very powerful computers that we didn't need to be connected to a mainframe, and they were inexpensive enough for individual users to have one on their desk, it was a very interesting time back in the 80s or so. Lots of fun games were played, lots of interesting business software was executed, and as that grew, teams of people, each with a PC on their desk, needed to share information, and that's where being connected to a server and a common place to do processing and store data was needed. And so we got into the client-server generation in the 90s. Eventually that grew to where we wanted distributed data. When Google was invented, we needed to have vast amounts of information at our fingertips that we could send messages across the internet to powerful distributed servers that could find what we were looking for and return to us. So this is where the cloud came from. The cloud is basically just a bunch of computers that are owned by somebody else that we can connect to and talk to and get data from and send data to. So then we have a generation of programs which we would call thin again, which is to say, I can send a lot of information to a server that's not running very much application code, and it can do really interesting things for us and not require a bunch of code on the server. So we also progress in the direction of microcontrollers. So usually we think of the chip that's in our personal computer. It's a central processing unit, a CPU chip. It's a big processor, very powerful, very advanced processor. But there are also little processors, and we call those microcontrollers. And they might live on something we would refer to as a Raspberry Pi type of a device. And you can use those little devices. For example, you could write a little security program and some sensors on a Raspberry Pi and attach it next to your door and keep your sister from coming into your door and set off an alarm when your sister comes through the doorway and things like that. But for very small individual solutions to the problems that are interesting to us for very low cost, a small microcontroller device and a few little inexpensive mass-produced sensors that we can get and connect to our microcontroller, and that's a fun area to go. The Internet of Things represents that generation of devices. Digital twins are basically taking those microcontroller-based devices and attaching them in the cloud to be able to, like if you owned a factory and you wanted to distribute a whole bunch of these sensors across your factory floor in order to return data from those sensors to one central place and be able to monitor it from a dashboard. Then digital twins and cloud-based services that we use to connect those microcontrollers to. So it's all very fascinating, and the only reason I go through this brief discussion of history is to show that it's all just code. It's all just instructions that we're writing for a computer to execute, but it's done in a variety of contexts. You can think of it like food in a way. There's food that, you can make a piece of toast in a toaster oven and butter it and have a glass of juice for breakfast. Or you can go to a restaurant and have that same toast and juice made by a chef behind the grill in a restaurant and delivered to your table by a waitress. You can go to, join the army and have mass produced for hundreds of troops, this piece of toast with some butter on it and a glass of juice. But it's all the same thing. It's just done in very different contexts. And the landscape of all the different kinds of hardware and kinds of software today is so diverse that it's really hard to even list all the ways that software can be used. So going back to one of my earlier points, there's no way that I can teach you how to write code for all of those contexts in one semester. So we're going to just start with the basics and learn how to write inputs, processes, and outputs over and over and over again in various ways, and use all of the basic techniques of a programming language like Python. And I just want to introduce you to all of those different things. One of the other misconceptions, I think, is that people think that if I become a programmer, I'm going to be locked into something, and that something is whatever their misconception is. And I want to open up your vision to realize that there are vast opportunities out there for people who know how to write software. So, just a brief introduction to that topic. So, in the realm of programming languages, we've talked about Python several times. I've got a list down there on the slide of many other of the programming languages that I'm familiar with to one level or another. But they all have strengths and weaknesses. They were all developed to fill a niche at the time, and they all follow different patterns, and they have similarities and differences. So I want to introduce you to what some of those similarities and differences are, again, so you can understand where Python fits into that, why we're using Python for this semester as opposed to one of these other very valuable, at least at one time, programming languages. So all the computers that we've talked about, they're all going to execute machine language code. They're all basically hexadecimal codes that we send to the processor that causes certain circuits to be activated and causes other things to occur. So the input is the code that we're going to give the processor. The processor may go out to memory to get additional input to bring in. It'll perform some calculation and it'll send the output out to some register or some other memory location. It's constantly doing that very simple and basic mundane task many, many times a second, and very accurately, we hope. Almost never failing to do the correct thing. But it all operates on machine code. We would refer to those also as low-level digital instructions. Okay, so if we were to sit here and teach you this semester on how to write machine code, you could do it. It's just going to be very tedious. My first job out of college, working for American Airlines, or TWA in Kansas City. TWA is an airline that doesn't exist anymore, but they did back in the 80s when I started my career. One of the initial jobs that they would give a new programmer on the staff was a support role. So they'd say, well, last night our big expensive computer crashed, and they would give me a printout about an inch thick of that green bar paper with the little holes on the side that came out of a tractor feed computer. It'd go green, white, green, white, green, white, so we called it green bar paper. And it would just be row after row of nothing but hexadecimal digits across the page. And my job was basically to interpret those instructions and figure out where the bug was and what the root cause was. it's a daunting task until you start realizing, well, if I understand what the processor is doing, I can reverse engineer. There's a register that says here's the address of the next instruction that was supposed to be executed. I can go to that location in memory, and if I know what the machine code instructions are, I can use that to say, okay, here's the instruction it was supposed to do next, but what about the one that it crashed on? So I have to back up in the memory and look for what that instruction was, the one that actually crashed. I can say, well, what memory was it referring to that it pulled in, that it did something it decided that it couldn't do or was invalid? I'd have to reverse engineer that. And that whole stack of paper was just for one problem. There may have been 10 different crashes last night. So as soon as I say, okay, well, here's what happened, they'll say, okay, thank you, and they'll hand me another one. Over and over and over for 8 hours a day is very tedious. And it's also, it doesn't mean that I would come up with the correct solution either. I might not accurately diagnose what the problem was. That happened once in a while too. That's saying, no, you're drawing the wrong conclusion. Here, let me go through this with you and teach you something else that you might not have known. But I was dealing with the machine language code directly at one point in my career, is the point. I'm happy that I don't have to do that anymore. I also had to do that when I was working on, later in my career, working on a 3D space game, because the graphics card had a very complicated graphics driver that our game software had to interface with, and often it would crash, and we had to dig into what was going on in the driver level, talking to the hardware, and figure out what the code had done wrong. And similar thing, a lot of that was looking at binary hexadecimal code, trying to deduce what happened. So we don't want to do that if we don't have to. It's costly. It takes a lot of time to learn that skill, and it's just not very fun. You burn programmers out if you make them do that a lot of years. So when we talk about these computer languages, these are meant for us humans to more easily encode our algorithms and provide them to the computer so that the computer can execute our instructions. Again, what about that first line where it says computers operate on machine code? So at some point we got to take our more easy to understand instructions and we got to convert them to machine code. And we do that in a number of different ways. This actually divides up many of the languages between compiled languages and interpreted languages. A compiled language is going to take our source code that we write, like our Python or our C++ code, and it's going to take that text file with our code in it, and it's going to compile it into a binary file, like a exe file. And that exe file is something that can be executed because it contains the machine language that the computer needs to execute. So C++ works that way. It compiles it directly into machine language. Python doesn't work that way. Python is more what we call an interpreted language. So in an interpreted language, you're executing the raw source code, the text. So if I take my Python text file that has my Python instructions in it, and I provide it to the Python interpreter, that interpreter is going to read my code one line at a time and convert that line to machine language and instruct and execute that line one at a time. There are pros and cons to that. The interpreted languages are generally easier to learn and easier to create quick solutions in. So time to market might be a factor. They're also easier to understand by people who really don't want to get in the weeds. C++ is a pretty complicated language to master, and so you might not need to master a programming language for the problem that you have. Often data mining careers, the people in those careers like languages like Python because it has a lot of the breadth of power and abilities to do computations that they need to access without the requirement that they dig in and learn the depths of a programming language in order to do it. C# and Java are in-between languages. They came up with a hybrid at some point where a C# or a Java class, you start with the source code, you write your source code, it's just a text file again, and then you compile it, but you don't directly get machine language code out of it. When you compile a Java or a C# program, you get what we call bytecode or intermediate language. And this intermediate language is something that looks like it's halfway between machine language and human readable. You could actually open up one of these intermediate language or bytecode files, and you could kind of decode it yourself and follow through what it's telling the computer to do or what it's going to tell the computer to do. But then we have a second piece of code. For Java, we call that the Java Virtual Machine. For C# we call that the .NET Runtime. And these pieces of software will take that bytecode or intermediate language and they will execute it. And the benefit there is, you might think, well, you've got the bad points of the compiled language and you've got the bad points of the interpreted language. Well, no, the way they did this intermediate language is so close to being understandable by the computer that it's almost instantaneous to interpret the bytecode at runtime. Also, the compiling step eliminates a lot of the syntax errors that you might see at runtime in a Python code program. So it's kind of a hybrid. So you got pure compiled languages that go straight from your source code to machine language like C++. You've got intermediate like Java and C# that compile your source code into intermediate code that's then executed by a runtime environment. And then you've got purely interpreted languages like Python or BASIC, where it just opens the text file one line at a time and the interpreter executes the code one line at a time. So that's the different kinds of languages out there. And they're good, and each one of them is meant for a different purpose. Your operating systems often are written in C++ so that they can be ultra fast, but they're also ultra complicated. Many of your modern application programs like Word, Excel, PowerPoint, etc. might be written in something like C# or Java. And like I said, the data mining folks that don't want to have to become a programmer expert, but they've got a job to do anyway that they can use programs to solve, will go more for something along the lines of an interpreted language like Python or BASIC, etc. Pascal, Fortran, and COBOL I throw on there because they're valid historical computer languages. In some cases they may still be used today. I think people still use COBOL, but COBOL's been around since the 70s, so it's a very it's got a long history. How about we say that? Yeah, so why so many? Well, like I said, there's pros and cons to each one. Each one of them fills a niche, or it wouldn't have gotten popular in the first place. We have all of these different variables, these dials that we can turn. Maybe one language is harder to write, but gives us faster programs like C++. Maybe one is easier to write, which means it's easier to learn. Maybe I need to learn this quickly, and I don't need to become an expert at it in order to solve the problem at hand. And you can go down each one of these. The compiled languages, I would say they tend to execute faster. You can produce faster code, which is the reason why C++ is the language that most computer games, Xbox, PlayStation games are going to be written in, because they need that power. They need to be able to leverage the hardware the most and produce the highest performing code. And then I like the intermediate languages because they provide that balance. To somebody that's a power programmer, power user of a programming language, you have all the power at your fingertips that you have with a C++ language, but you have a lot of the modern conveniences available for productivity that one of the interpreted languages might offer. So Java and C# strike a really good balance for people. So if you're going to continue on your path as a programmer, that's what I would say is Next step would be to go from Python to either Java or C# or both. And then from there, I would make sure that you get some C++ under your belt before you finish your academic career. Hope that helps. All right, as we're writing our code, we're going to hear this word syntax. So all syntax means is that your language has rules, and those rules are the syntax of that language. So if you've ever heard Yoda speak in Star Wars, the backwards, reverse, switching words around way that Yoda has of speaking, why is that quotable at all? Why would anybody even remember? It's because he doesn't follow the rules. You can still kind of sort of understand what he's saying eventually, but you have to think about it. He's not following the rules of the language. And so same with the computer, except that the computer doesn't let you get away with it. The interpreter or the compiler is not going to say, wow, that was weird, but I think I know what you meant, so I'm going to do this. The joke that we have with computer programs is, darn that computer, it did exactly what I told it to, but not what I wanted. And that happens often when you're early, in your career as a programmer. So we're going to focus on Python. So one of the things that we're going to do is learn the rules of the Python language. And a syntax error is when we fail to follow one of those language rules, which causes our program not to be able to be run. Contrasting that with a logic error is, well, it follows the rules of the language perfectly. It just does not produce the correct results. So the example I have there, if the horse has already run away, lock the barn door. Well, we would say, yeah, I understand exactly what that sentence says, but you got something wrong there, dude. You should lock the barn door before the horse tries to run away. So we would correct the logic of that in order to produce the correct outcome. And you can see the other examples there. Okay, another thing about our computer hardware is the idea of the circuitry. So all of the computers that we're talking about here are built on top of some form of silicon or copper or combination thereof, where electrical signals are bouncing back and forth and doing interesting things. So if we have a piece of circuitry that I can turn the power on and I can send some electricity to part of that circuit and it sets it to a particular state, and then later I can come back and check that state and I get the value back, the state that I put it in. If I change the state, again I can come back and check it, and now it has the changed state, and I can go back and forth on that all I want to. That memory, that's what we call memory, that kind of a circuit. And there's this term called volatile. So if I have memory that is volatile, that means if I turn the power off, it loses all of its state and I can't rely on what state it's in anymore. So volatile random access memory is just our plain old memory that we have in every one of our computers. They call it random access because I have, let's say, 4 gigabytes of RAM on my computer, and I can access any byte of that entire 4 gigabytes anytime I need to. So that's why we call it random access. They call it that. It's not so significant today, but early in my career, most of the storage that I had was sequential access memory, which meant if I wanted to read the 100th byte of the memory, I had to start at byte 1 and push the read head forward to get to the 100th byte and then read it, and then bring the head back to the beginning so that the next person could read what they wanted to. It was very inefficient. So having random access memory come along was a huge innovation and made a big difference in the performance and effectiveness of our software. Because some algorithms were so slow using sequential access memory that we didn't even write them. It was pointless. ROM is similar. It's read-only memory as opposed to random access memory. read-only memory is what it says. So, for example, the settings in your car that control the way the mileage and power settings are configured, you put the chip into a certain mode, you write the data to it, and it stays that way until some other future date and time. Generally, you can't change it. You can read from it, but you can't write to it until you put it into the special mode that you can do as a manufacturer. And it's not really architected to be able to put it into that mode very often. Some read-only memory is you can only write to it once, period. Like a DVD or a CD player. That disc, you can write to it once, and that's it. It's hard-coded, and it can't be changed ever. You throw it away and get another one because you can't rewrite that first one. And then they also have read-writable CDs and DVDs. So, a lot of evolution has happened, but if we come back to just the basic terminology, random access is just plain old memory. Read-only memory is write once, read many times type of memory. I think that's all the concepts on here. It's either read-only or it's writable. It's volatile or it's not. Random access. Yeah, I think I hit all that. So those are many of the different kinds of memory that we have. If you've been paying attention to the industry, Microsoft has been talking about this technology for a while that's a very, very high capacity storage. I don't know if you know this or not, but your typical CD or DVD player, the discs that you use in those devices, they don't last forever. They don't even last what I would consider a long time. I think now you can get long-lasting discs, but those discs, you may go back to, especially if something's been left out in the sun, you may go back out to those discs 5 or 6 years later and realize that, it's just gibberish now. There's so many failures on the disc that I can't even read it anymore. But what if we wanted to take like every piece of information that's currently accessible via Google and we want to store it for 100 years or longer? How would we do that? And so basically Microsoft's been experimenting with these Lucite cubes about this big, where they use different lasers and they actually physically etch notches inside the disk in 3 dimensions, and that way it's a physical alteration of the cube structure that can be read later by other lasers. And it's write once, read many times, so it's read-only memory, but that physical cube should last a long time unless it's subjected to high enough heat to damage the device or something else. So we don't really have commonly available devices or the media, the actual cubes, in order to write things to. But for people like Microsoft and Amazon that run large data centers and have to manage large quantities of data, this may be a very economical way to do it at some point, just being experimented with. So another thing I want to mention about handling memory comes where we talk about an assignment statement. So when we think about how computers handle data, I've got an example here of an expression, 5 times 3 plus 2. Now, if you and I look at that, we can probably agree that we mean to multiply 5 times 3 and add 2 to it, so 17. So, we would all assume that that's what we meant by that expression. Well, if I type that into a Python program, 5 times 3 plus 2, and hit enter, it's going to say, 5 times 3 plus 2, and I evaluated that expression. I came up with a value of 17. So what? What did you want me to do with it? You just said it, and it's valid, but you didn't tell me anything to do with it. So to be useful, what we would usually do is, instead of just making an expression, we would create an assignment statement. So when you see something like answer equals 5 times 3 plus 2, that tells the computer, okay, evaluate the expression on the right side of the equal sign, 5 times 3 plus 2, I get 17, and store it inside the variable answer. That's what that means. Now, if you've ever had a math class and you've seen formulas like x squared plus 2x plus 4 equals 0, or y equals mx plus b, or e equals mc squared, separate that all out in your head. That's what you talk about, and that's how you speak in your math class. In your computer class, we speak in terms of assignment statements. So we have a variable name equals and an expression. So the way you properly read this is take 5 times 3 plus 2, evaluate it, get the result, and store it into the variable called answer. Now the next line is a little different. The next line is a print statement. It says print 5 times 3 plus 2. Okay, well, it's not an assignment statement, but similarly we would say evaluate the expression 5 times 3 plus 2, 17, and print it. So the print statement is going to take some kind of an expression, and it's going to display 17 on the screen. So similar to math, don't be confused by the fact that you see some similarities with math and it behaves in some ways like math. I mean, the way we're evaluating an expression definitely follows mathematical rules, but you need to start thinking in terms of what this computer language is trying to say, and how to do it. If you go to France and you're trying to figure out which train goes to Nice, you need to understand the rules of French, and for the problem that you're trying to solve, figure out a way in that language to say what you want to say. So if I wanted to calculate 17 and use it for something later, I would evaluate the expression that comes up with 17, and I would store that in a variable called answer. Okay, so software development lifecycle is the next thing I wanted to introduce you to. So you also see that in the book called Program Development Lifecycle, I think. It involves lots of skills and perhaps even a whole team of people doing complementary tasks in order to produce a version of software that's meant to ship, at which point you start iterating again. You get another list of features or another list of bugs that have been reported, and you start figuring out how to integrate those into your software, get it to build, get it to run, get it to debug it, fix the problems with it, get it ready to ship that version of it, and you iterate and you start doing it again. But when we talk about the software development lifecycle, we're referring to all of those steps that you do for one version of the source code to get it from conception all the way to the customer's hands. So for us, like I said, we're going to talk about the homework life cycle. And so for the homework life cycle, what we're going to typically do is we're going to be given an assignment and we're going to design it. That might involve IPO diagram, might involve flowchart, pseudocode, and then once we have a plan in place for how we want to write our program, how we want to solve the problem, then we'll produce the code, the Python or whatever language we're using that can be executed on the computer, and then we're going to test the program. So when we go to initially test the program, if it's a compiled language, we're going to compile the program. Maybe we have some syntax errors, we have to fix the syntax errors, and if it's an interpreted, we'll take the next step of running it. Maybe we find syntax and logic errors at the same time at that point. But here's one of the points that I want to make is when we're testing our program, like it was not uncommon in my career for a programmer to say, hey, by the way, I finished this task that you gave me, and don't worry about testing it. I already went through and I tested it. I didn't put a lot of stock when developers said that kind of thing to me, because I saw too many times where a programmer would write some code and claim that it was finished when it didn't even compile. Okay, so if you give me code that doesn't even compile, I'm pretty sure you didn't test it. Because if you can't compile it, you can't run it. If you can't run it, you can't test it. And so I saw that happen too many times to rely on anything they said. I usually had to go verify it myself, okay, to be sure. And so even if it compiles, that doesn't mean you don't have any logic errors in it. So you still have to take a program that compiles correctly and run it through some data. And what I also see programmers do a lot is they will say, well, I used the data that you told me to test it with 5 and 3, and I tested it with 5 and 3, and it worked. It printed 8, so I assumed it was working correctly. Well, what if you give it a negative number? What if you give it 0? What if, there's all kind. What if you type in cat instead of 5? What does your program do? The breadth of test cases that you use with your program is important in order to produce a reliable solution. Even on the compiling thing, what often happens with programmers is they say, okay, great, I've been working on this all afternoon, it's getting late, I need to turn it in. It works. I've tested it, it works. Oh, by the way, I want to go change this one little prompt message and make the prompt message kind of more friendly, a little nicer prompt message. Or you find a misspelling in something and you think, I'm just going to go change the misspelling and correct that. But they assume that what they did was correct, and I don't need to recompile it because all I did was fix a misspelling, not realizing that they did that fix incorrectly, or it broke something else some other place, and they make assumptions. Okay, it isn't intentional. It isn't that they're trying to be careless. It's just that they're following an unreliable pattern, unreliable behavior, an unreliable homework development cycle, if you will. So what I will suggest that you do in order to get close to full credit, the closest as you can get, is you design your program well, you write your flowchart or your pseudocode or both, whatever you're asked to do, you produce your code, you make sure that it compiles, you test it with a variety of pieces of data, and if you make any changes to it before you turn it in, you go back and you recheck that it compiles, you retest it with the data. Now that you have confidence that it's working correctly, then you turn it in. Okay? Yeah, testing, there's this axiom that says the bugs are cheaper the earlier they're found. I've heard that debated quite a bit, but the principle is sound. If you find a problem with your design while you're doing your pseudocode and you fix it right there, well, good, you saved yourself the trouble of writing a bunch of code based on that flawed design, and you didn't waste time later. So it makes sense. It's common sense. It's intuitive, I guess I would say, that it's true, but we're not trying to come up with precise amounts that you saved yourself by finding it early. It just, if you do your design work and you find problems there, you're going to produce better code is the principle. The idea of desk checking is you don't even need the computer yet. If you take a piece of paper and you write out your pseudocode on the piece of paper, you can go through and do some desk checking of your program in order to make sure that it's working in your head before you even try to test it with the computer. I do that quite a bit. Or if I get a printout of a piece of code that I've been told has a bug in it, I can desk check it on my own, just going through it in my head with a variety of test cases on paper to make sure that that I know how that code works. I'll also do that quite a bit when I'm introduced to a new part of the code. So if I'm told in my job that I have to start working on this code, I'll just start looking through the source code and in my head try to follow through what it's doing with various pieces of data just to understand it better. And I really like the tools that we have available to us now, Flowgorithm and Raptor. I wish we had those earlier in my career. I probably would have made a lot of use out of them. The great thing about those tools is they let you create your flowchart diagram and then test it. You can actually execute your flowchart to see what your logic is going to do, if it's going to be correct or not. That's pretty neat to me. Do you have to use those tools to do your flowcharts? Well, I expect you to turn in a flowchart, but if you take a piece of paper and you scribble your flowchart on a piece of paper and you take a picture of it with your phone and upload the image and turn in the image, it's possible to create a correct flowchart that way. I would say it's a lot easier to get full credit for your flowchart if you use one of these tools, because they make you do it correctly and they let you test it before you say you're done with it. If you're scribbling it on a piece of paper, what's the odds that you're going to leave out one of the little arrows, or you're not going to connect two of the boxes together, or you're going to use the wrong shape, or you're going to make a mistake somehow. So that's the way I say it, is you're much more likely to get full credit for your flowchart if you use one of these tools. I've seen students be less successful when they go use something like Paintbrush, or one of these graphics editing tools, or Lucidchart, or something else that manually lets you create sometimes very attractive but sometimes very wrong flowcharts. So if you know what you're doing, you can use whatever tool is accessible to you in order to create your flowcharts. Dial your own level of pain there. If you want to get full credit, you can take the risks that you choose to take. So we mentioned debugging. So after you've coded it, make sure that you run it with many different inputs. If you're, just think, what is it going to do if I do something that a malicious user might do? What might a malicious user try to do? When I talk about one set of data, that's typically what I refer to as the happy path. So if I use in my example, okay, here's the exercise, you're supposed to add these two numbers together and print the result. Okay, for example, if you enter 5 and 3, it should print 8. Well, that's the happy path example. So if you only test with 5 and 3, you're only testing the happy path. What about -4 and the square root of 2? And what about if I enter cat, or I don't enter anything and just hit enter, right? All of these different behaviors you want to test for, and just make sure that you understand how your program is running. And that's pretty much it for this class. I appreciate you hanging in there. In the beginning there's a lot of information to download in Grok, but there's a lot to reinforce, and I think that the more we get into it and the more you get the hands-on and you're able to do the exercises on your own, the more it's going to make sense. And I'm looking forward to a fun semester with you all, and good luck, and I'll see you again next time.